Hello, today we're going to apply what you know about tau equals VQ over IT on a U-beam cross-section to find the shear stress acting across the face and through the cross-section. So here we have our cross-section. The flange is 1 inch thick, it's 5 inches tall, and 4 inches wide. So we're going to be finding the shear stress at several points on this cross-section. Point A, which is across two sections as you can see here, B, and C. We're going to use several methods to find the shear stress using several different combinations of areas. First, at point A, we're going to be using one section, two sections, the opposite of the first section, and the opposite of the two sections. We're then going to be looking at point B, both the bottom portion and the top portion. And finally, we're going to look at point C. We're going to start with the left portion, then the right portion, and then finally a cut that is in the center of the cross-section. The first thing we need to do is find the center of area of our cross-section. As you can see here, we've placed a coordinate axis with n as the vertical axis and m as the horizontal axis. We're going to find the sum of NIAI, or the sum of each area multiplied by its distance from an axis. Now, we are not going to do this for the n-axis because due to symmetry, we know that the center of area will be in the center of the shape from left to right. However, we don't know where the center of area is from top to bottom, so we're going to sum about the m-axis. So the first area we have is this area here in purple. It is 3.5 inches up from the m-axis and is 3 inches by 1 inch for area. We have a similar green area that is also 3.5 inches up and 3 inch by 1 inch. Finally, we have an area that is 1 inch up that is 4 inches by 2 inches. When we sum all these, we get that the sum of NIAI is equal to 29 inches cubed. Now we need to find the total area for the cross-section. So we can do this by adding the two shapes that are 3 inch by 1 inch, the purple and green, and also add that to the 4 inch by 2 inch section in blue. When we do this, we get that AI is equal to 14 inches squared. Now, to find where the center of area is about the m-axis, we will take the NIAI term and divide it by the AI term, or the NIAI term divided by the total area. So that ends up being 29 inches cubed divided by 14 inches squared, which will give us a n bar, or center of area, of 2.07 inches above the m-axis. So now that we know where our center of area is, shown here, the neutral axis horizontal, we now need to find the moment of inertia. Now normally for a shape, and specifically a rectangle, we would use the equation bh cubed over 12 to find the moment of inertia. However, these rectangles are offset from the axis, so we're going to have a term a dx squared involved, and we have that for each of these terms as shown. Now if you're to input all of the information, their widths, heights, and distances from the x-axis, or in this case the z-axis, you will find that the total moment of inertia is about equal to 29.2 inches to the fourth. Alright, so we're going to start with cut A method 1. As you can see here, here's our cross section with our axes aligned at the center of area, with the neutral axis as that red line you see running along the z-axis. The center of area is 2.07 inches up from the bottom of the shape, and here's our section here. Its center of area is 2.18 inches from the neutral axis. It has dimensions of 1 inch by 1.5 inches, and it has a depth delta x. Running along the face, we have tau xy, and along the bottom, tau yx. So we're going to use x equilibrium to find out what tau xy and tau yx are. So we know that tau yx is equal to VQ over IT. The shear force across the section is 500 pounds, the thickness of our piece is 1 inch, and the moment of inertia is 29.2 inches, and that moment of inertia is for the shape as a whole. Next, we need to find Q for our section. So for this, we have a 1.5 inch by 1 inch section, and the distance from the neutral axis to the center of that area is 2.18 inches. And when we do this, we get 3.27 inches cubed as our Q value. Now, if we plug these numbers into the VQ over IT equation, we see that we get that tau yx is about 56 psi. And from equilibrium, we know that tau yx is equal to tau xy. Okay, so here's our section as we saw in the previous slide. However, we're going to look at the cut from the other direction this time. As before, tau xy is running down the face of the shape, but tau yx is in the opposite direction, but this is only to maintain equilibrium. For convention, Q will be negative above the neutral axis and positive below the neutral axis. We're going to use x equilibrium to solve for the shear stress on this section. As before, tau yx equals VQ over IT. The shear force is 500 pounds, the thickness is 1 inch, and the moment of inertia is 29.2 inches to the fourth. For this, calculating Q is just a little more complicated, but not too hard. So we're going to start with the pieces that are above the neutral axis. So we have the smaller rectangle and a larger rectangle. The smaller rectangle has dimensions of 1.43 inches by 1 inch, and its center is 0.715 inches up from the neutral axis. We're then going to have to add the larger rectangle with dimensions 2.93 inches by 1 inch with a distance of 1.465 inches to its center. So those are the negative terms you see in the Q calculation. Now we're going to drop below the neutral axis and add the positive terms. We have two sections that are 0.07 inches by 1 inch, and their centers are 0.035 inches away from the neutral axis. We also have that larger section that is 4 inches by 2 inch that has its center 1.07 inches away from the neutral axis. When we add all these together, we get that Q is equal to 3.25 inches cubed. Now, in our tau equation, we put in all of these numbers and we find that tau yx is roughly equal to 56 psi, and that tau yx is equal to tau xy. As we saw before, this value for tau is actually just about the same as it was for the other section. In fact, it is the same. So this time we're going to take that cut and extend it all the way across the top of the section. So it'll look something like this. We're then left with two sections that are 1 inch by 1.5 inches that are 2.18 inches up from the neutral axis. As before, tau xy is running down the face of the section, and we're going to use x equilibrium to solve for that shear stress. So, as before, tau yx equals VQ over AT, as it always does. The shear force is 500 pounds. The thickness this time is 2 inches. That's to account for both sections. So there's 1 inch from each section. The total T is 2 inches. That's the thickness being cut through. And as always, moment of inertia is 29.2 inches to the fourth. This time for Q, we have two sections that are 1.5 inches by 1 inch in area, and they are 2.18 inches up from the neutral axis, giving us a Q value of 6.54 inches to the third. If we use our shear stress equation, we find that the shear stress is roughly 56 psi. Okay, so what if this time, as before, we look at the bottom part of this cut? The cut that looks something like this, so it's the opposite of the previous cut. As before, Q is negative above the neutral axis and positive below the neutral axis. Shear stress is running down the face of the section, and we're going to use x equilibrium to solve for that shear stress. As before, tau yx is equal to VQ over IT. The shear force is 500 pounds. The thickness is still 2 inches because we've cut through 2 inches of material, and the moment of inertia is 29.2 inches to the fourth. So Q is a lot more complicated than it was previously, but not too bad nonetheless. So we're going to start above the neutral axis. We have two sections that are 1.43 inches by 1 inch that are 0.715 inches up from the neutral axis. Now we're going to look below the neutral axis. We have two sections that are 0.07 inches by 1 inch that are 0.035 inches away from the neutral axis. We also have a section that is 4.2 inches down 1.07 inches from the neutral axis. When we add all these together, we get that Q for this particular section is 6.52 inches to the third. Plugging these in the shear stress equation, we get that the shear stress is again equal to about 56 psi. And that tau yx is of course equal to tau xy. Now what we've seen here is that either way you make the cut, as long as you're cutting through the same section, you're going to get the same shear value. It doesn't matter if you look at the top section or the bottom section of that cut, as long as it's the same cut being made, you will get the same shear stress value. Okay, so now we're going to take a look at cut B. So we have our cross section here as before. 2.07 inches up is the centroid, and the width of the section is 4 inches. So the section we're going to be looking at is this cut that went across the bottom of the section. So standard delta x for its thickness, and for its height is 1 inch. So tau is going to be running across the surface like this. So now we want to use our x equilibrium to figure out what that tau is. So as before, tau yx is equal to vq over it. And we have a shear force of 500 pounds, a thickness of 4 inches, and our moment of inertia of, again, 29.2 inches to the fourth. So for this section, our Q is 4 inches by 1 inch, that's the area, and this section we're looking at the bottom here is 1.57 inches from the centroid of the overall section to its centroid, and that gives us a Q of 6.28 inches to the third. When you plug this into our tau equation, we get that the tau, or shear stress, on the y face in the x direction, yx, is equal to about 26.9 psi. And as before, tau yx is equal to tau xy. So now we're going to look at the top part of the cut. So that'll look something like this for point B. So as before, we have tau yx running down the face of the section, and tau yx is going the opposite direction of the way it was before. And similarly, we will use x equilibrium to solve for tau yx and tau xy. So as before, tau yx is equal to vq over it. Our shear force is 500 pounds. Our thickness for the section through the cut is 4 inches, and our moment of inertia is 29.2 inches to the fourth. Now, as with some of our previous sections, Q can be a little complicated, but we'll take it step by step and it won't be too bad. So we're first going to look above the neutral axis. That's where Q is negative. So we have two sections that are 2.93 inches by 1 inch, and their centers are both 1.465 inches above the neutral axis. So that takes care of the negative portions. Now we're going to look below the neutral axis. For this, we have two sections that are 0.07 inches by 1 inch, and their centers are 0.035 inches down from the neutral axis. And then we also have one more section that is 4 inch by 1 inch by 0.57 inches down. Now, when we sum all of these, we get that Q for this section is negative 6.3 inches to the third. Now, when we plug all these numbers into our tau yx equation, we get that tau yx is approximately 26.97 psi. Now, we took that negative and we used the absolute value to figure out what tau yx is, so that it all works out. And as before, tau yx is equal to tau xy. Now we're going to take a look at our third and final cut, cut C. So, on our section, it'll look a little bit like this. The cut is made 1.25 inches from the left side of the cut, and the thickness is delta x. Now, the shear stress running across the surface will look something like this. So now that we switched planes, we switched directions with our shear stress. But not to worry, it can still be found using x equilibrium, and tau equals vq over it. As before, the shear force is 500 pounds, the thickness of the cut is 2 inches, and the moment of inertia is 29.2 inches to the fourth. And now we need to find Q for this section. So as before, we're going to start by taking it piece by piece. We're going to start with the piece above the neutral axis, so that's the negative portion. So we have minus 2.93 inches by 1 inch, the dimensions of the area of that section above the neutral axis, and its center is 1.465 inches away from the neutral axis. Now that we've found that, we can look at the sections below the neutral axis. So we have one section that is 0.07 inches by 1 inch, and its center is 0.035 inches away from the neutral axis. And we also have a section that is 2 inches by 1.25 inches, that its center is 1.07 inches away from the neutral axis. When we sum all of these together, we get that Q is equal to minus 1.615 inches to the third. We're then going to plug that into the tau equation and get that tau, or shear stress, is roughly equal to 13.83 psi. And as before, tau zx is equal to tau xz. Alright, so now we're going to look at the cut through C from the other side. So its section will look a little bit like this. So tau zx is now switched in direction so that it equals and opposes the other tau zx. However, tau xz is running in the same direction as it was before. So as before, we're going to use x equilibrium to solve this with tau equals vq over it. As before, the shear force is 500 pounds, the thickness is 2 inches, and the moment of inertia is 29.2 inches to the fourth. So to find our Q, we're going to use Q is negative above the neutral axis and Q is positive below the neutral axis, as before. So we're going to start with the section above the neutral axis. So its dimensions are 2.93 inches by 1 inch, and its center is about 1.465 inches above the neutral axis. As for the sections below, we have a section that is 0.07 inches by 1 inch. That center is 0.035 inches below the neutral axis. And we also have a section that's 2.75 inches by 2 inches. That center is 1.07 inches below the neutral axis. When we sum all these together, we get that Q is about equal to 1.595 inches to the third. When we plug this into our tau equation, we get that tau is about equal to 13.66 psi. And as before, tau zx is equal to tau xz. Alright, so now we're going to look at the third and final method for evaluating the shear stress at cut C. So instead of taking just one cut through the section, we're actually going to take 2 cuts. So it'll look something like this. The shear stress will look like so on the section, and we're going to use x equilibrium to solve as we have before, and tau equals VQ over IT. The shear force will be 500 pounds, the thickness will be 4 inches because we're cutting through 4 inches of material, and the moment of inertia will be 29.2 inches to the fourth. Now we need to find Q for this section, so we have just one section this time below the neutral axis, so it'll be positive. Its dimensions are 1.5 inches by 2 inches, and its center is 1.07 inches away from the neutral axis. Pretty simple. So Q equals 3.21 inches to the third. We're going to plug all these numbers into our tau equation and find that tau is equal to 13.7 psi. And, as usual, tau zx is equal to tau xz. Now, if you've noticed anything about all these different cuts throughout A, B, and C, you notice that no matter how you cut it or how you kind of look at the top section or the bottom section, you'll see that the shear stress will be equal at that plane. So as long as you use x equilibrium, tau equals VQ over IT, you'll be able to find your shear stress.